Okay, maybe just this I can read. Thank you for watching this video. And that's for me. Wassalamualaikum warahmatullahi wabarakatuh. See you. Assalamualaikum warahmatullahi wabarakatuh. Hello everyone. Good night. Let me introduce myself. My name is Nuril Firdausiah. You can call me Firda. I'm from physics major. Especially I'm from Overingen. Okay, in this beautiful night, I will complete my assignment at English for physics subject. And okay, now in this video, I will read the fundamentals of physics book at page 23 until 24. Okay, let's begin it. Constant acceleration. Learning objective. After reading this module, you should be able to 2.13. For constant acceleration, apply the relationship between position, displacement, velocity, acceleration, and elapsed time. Table 2 until 1 in bracket. 2.14. Calculate a particle's change in velocity by integrating its acceleration function with respect to time. 2.15. Calculate a particle's change in position by integrating its velocity function with respect to time. Key ideas. The following 5 equations describe the motion of a particle with constant acceleration. V equal V0 plus A times T. V to the 2 equal V0 to the 2 plus 2 times A x minus x0 in bracket. X minus x0 equal V0 times T plus 1/2 times A times T to the 2. X minus x0 equal 1/2 times V0 plus V in bracket times T. X minus x0 equal V times T minus 1/2 times E times 2 to the 2. These are not valid when the acceleration is not constant. Constant acceleration, a special case. In many types of motion, the acceleration is either constant or approximately so. For example, you may accelerate a car at an approximately constant rate when a traffic light turns from red to green. Then graph of your position, velocity, and acceleration will resemble those in Fig. 2 until 9. Note that A T in Fig. 2 until 8 until 9 C is constant, which requires that Vt in Fig. 2 until 9b have a constant slope. Later, when you brought the car to a stop, the acceleration or deceleration in common language might also be approximately constant. Such cases are so common that a special set of equations has been derived or dealing with them. One approach to the derivation of these equations is given in this section. a second approach is given to the next sections throughout both sections, and later when you work on the homework problems, keep in mind that these equations are valid only for constant acceleration or situation in which you can approximate the acceleration as being constant. In brackets, first basic equations first basic equation. When the acceleration is constant, the average acceleration and instantaneous acceleration are equal, and we can write ak dot 2 until 7 with some change in notation as a equal a Vg equal v minus v0 over t minus 0. Here, v0 is the velocity at time t equal 0, and v is the velocity at any later time t. We can recast these equations, we can recast this equation as v equal v0 plus a times t. As a check, note that this equation reduces to v equal v0 for t equal 0. As a further check, take the derivative of ak dot 2 until 11, doing so yields dv over dt equal a, which is the definition of a figure 2 until 9b shows a plot of ak dot 2 until 11, the function. The function is linear and thus the plot is a straight line. Second basic equation. In a similar manner, we can rewrite ak dot 2 until 2 with a few changes in notation as Vg equal x minus x0 over t minus 0, and then as x equal x0 plus x equal x plus v avg times t, in which x0 is the position of the particle at t equal 0, and vavg is the average velocity between t equal 0 and a later time t. For the linear velocity function in ak dot 2 until 11, the average velocity over any time interval, say from t equal 0 to a later time t, in brackets, is the average of the velocity at the is the average of the velocity at the beginning of the interval equal v0 in bracket, and the velocity at the end of the interval equal v in brackets for the interval from t equal 0 to the later time t. Then the average velocity is vavg equal 1/2 times v0 plus v in brackets. Substituting the right side of ak dot 2 until 11 for v yields, after a little rearrangement, vavg equal v0 plus 1/2 times a times t. Finally, substituting ak dot 2 until 14 into ak dot 2 until 12 yet x minus x0 equal v0 times t plus 1/2 times a times t to the 2. As a check, note that putting t equal o yields x equal x0 as it must. As a further check, taking the derivative of ak dot 2 until 15 yields ak dot 2 until 12 again as it must. Figure 2 until 9a shows a plot of ak dot 2 until 15. That function is quadratic and thus the plot is curved. Three other equation 2 until 11 and 2 until 15 are the basic equations for constant acceleration. They can be used to solve any constant acceleration problem in this book. However, we can derive other equations that might prove useful certainly specific situations. First, note that as many as 5 quantities can possibly be involved in any problem about constant acceleration, namely x minus x0, v, t, a, and v0. Usually, one of these quantities is not involved in the problem either as a given or as a noun. We are then presented with three of the remaining quantities and asked to find the fourth. Equations 2 until 11 and 2 until 15 each contain 4 of these quantities but not the same 4. In ak dot 2 until 11, the missing ingredient is the displacement x minus x0. In ak dot 2 until 15, it is the velocity v. These two equations can also be combined in three ways to yield three additional equations, each of which involves a different missing variable. First, we can eliminate t to obtain v to the 2 equal v0 to the 2 plus 2 times a times x minus x0 in brackets. This equation is useful if we do not know t and are not required to find it. Second, we can eliminate the acceleration a between aks dot 2 until 11 and 2 until 15 to produce an equation in which a does not appear. X minus x0 is 1/2 times v0 plus v in brackets times t. Finally, we can eliminate v0, obtaining x minus x0 equal v times t minus 1/2 times a times t to the 2. Note the subtle difference between this equation and a key dot 2 until 15 when involves the initial when involves the initial velocity v0, the other involves the velocity v at time t. Table 2 until 1 lists the basic constant acceleration equations a key c dot 2 until 11 and 2 until 15 in bracket, as well as the specialization equation that we have derived. To solve a simple constant acceleration problem, you can usually use an equation from this list. If you have the list with you in bracket, just an equation for which the only unknown variable is the variable requested in the problem. A simpler plan is to remember only AKC dot 2 until 11 and 2 until 15 and then solve them as simultaneous and then solve them as simultaneous equation whenever needed. Okay, maybe just this I can read. Thank you for watching this video, and that's for me. Wassalamualaikum warahmatullahi wabarakatuh. See you.